There are other areas on this diagram where the airflow is the complete opposite. If we examine the area between the Hadley and Ferrel cells, we can see that this time the airflow in the upper atmosphere is converging and descending. Then, upon reaching the surface, the air diverges. This pattern of airflow results in a net gain of air in the column shown. This is because the air at the surface is leaving more slowly because of surface friction. But the convergence of air at the tropopause is much more active due to the lack of friction. We have learnt from previous lessons that a net gain of air increases the weight of the atmosphere against the surface. Therefore, a high pressure zone is created. The high pressure systems which are found in this region are called the subtropical highs. We saw these before in the lesson on pressure systems, where they were called warm anticyclones. An example of a subtropical high lies in the North Atlantic and is known as the Azores high pressure system. There are two other regions where we see the same flow of air as the subtropical highs. If you look over the poles, we can see converging upper air and diverging surface flow. As we know, this results in a net gain of air, and therefore high-pressure systems are created. These are known as the polar highs. Looking at the diagram as a whole, we can see that just from the global air circulation pattern, we have managed to construct a global pressure pattern. Next, we will look at the surface wind flow across the globe using the pressure systems and our knowledge of surface wind theory. Going back to examine the area on the surface within the Hadley cells, it is obvious here and here that air is moving from the subtropical high and into the ITCZ. But if you remember from wind theory, the air doesn't flow directly from high to low pressures. If we examine the area in the northern hemisphere between the subtropical high and the ITCZ, we know that the Coriolis effect will deflect this flow of air to the right, as shown. In the southern hemisphere, the air moving into the ITCZ is this time deflected to the left. These winds are known as the northeasterly and southeasterly trade winds. They will tend to be stronger over the sea than over the land because of reduced surface friction. When the trade winds converge, they tend to create a region where the wind is light and very variable. These regions are common over the eastern parts of oceans and are known as the doldrums. Looking at slightly higher latitudes, let's now look at what we might expect the wind to be in the region of the subtropical highs. We know that in general, the isobar spacing in high-pressure systems is quite large, and therefore the pressure gradient forces are very weak. In these areas, the surface winds are generally light and variable. In the Atlantic, these areas of light winds underneath the subtropical highs are called the horse latitudes. Looking to even higher latitudes, let's now look at the area between the subtropical highs and the polar front depressions. Looking at the side view, we can see a flow of air along the surface from the high to the low. However, only a very small proportion of air experiences this flow. The Coriolis effect is stronger here, and much greater deflection will be observed. In the northern hemisphere, the air flowing to the low pressure will be deflected to the right. As a result, the major flow of air will be westerly or southwesterly. In the northern hemisphere, this flow is massively disturbed by the major land masses, and large changes in speed and direction can occur. The surface winds here are generally considered to be variable westerlies. In the southern hemisphere, as the air moves towards the low, it will be deflected to the left by the Coriolis effect, and the surface winds will be westerly. However, there is very little land or friction to impede this surface westerly flow. As a result, these winds are stronger and more regular than those at the same latitude in the northern hemisphere. These strong westerlies in the southern hemisphere are called by the latitudes where they are found, namely the Roaring Forties and Furious Fifties. The surface winds around the polar front depressions are very variable, because the polar front depressions themselves are very mobile. Next we will look at the surface winds between the polar front depressions and polar highs. Looking at the side view, we can again see airflow from the high to the low. But like before, very little air flows in this manner. Again, there is deflection from the Coriolis effect, and the resulting wind will be easterly in this area. Around the Antarctic Peninsula in the winter months, these easterly winds can get very strong, averaging up to 100 knots for days on end. The winds within the polar highs themselves should in general be fairly light, but the very mobile polar front depressions can still penetrate through the high pressure. If they do, the isobars tighten and the wind speeds increase dramatically.